Imagine, for a moment, standing in a vast plain under a sky so dark and deep that the stars themselves seem like distant whispers, faint echoes of light traveling billions of years just to reach your eyes. This is the canvas on which the story of our universe unfolds. A story that stretches across unimaginable spans of time, beginning nearly 13.8 billion years ago. Setting the stage for our journey into understanding whether the first planets came before the first galaxies requires us to immerse ourselves in this cosmos of deep time, a silent theater of creation and transformation, where the very fabric of space and time took shape. The concept of deep time is profound. It refers not merely to long periods, but to epochs so extended and alien that they challenge our intuitive grasp of history. Human history, in comparison, is a brief flicker. The Earth itself is about 4.5 billion years old, and yet the universe predates it by more than twice that age. The story we are about to explore begins well before the formation of our solar system, before even the first galaxies lit up the darkness. We start, of course, with the Big Bang, the primordial event that set all matter, energy, space, and time into motion. Around 13.8 billion years ago, an immensely hot, dense state rapidly expanded, cooling as it did so. This expansion is ongoing, with the cosmos still stretching out today. But the immediate aftermath was a universe filled with a glowing plasma of elementary particles, too hot for atoms to form. It was a time of incredible energies, but no stars, no galaxies, and certainly no planets. At least not yet. This early period is often called the primordial soup, a seething broth of protons, neutrons, electrons, photons, and neutrinos caught in a high-energy dance. The temperature was so extreme that any atoms that formed were torn apart instantly by the intense radiation. This delicate and chaotic beginning set the conditions for what would come next, but it took hundreds of thousands of years before matter could cool enough to allow atoms to stabilize. As the universe expanded and cooled further, it entered what we call the epoch of recombination, roughly 370,000 years after the Big Bang. This is when electrons combined with protons and helium nuclei to form the first neutral atoms, predominantly hydrogen and helium. The universe became transparent for the first time, allowing photons to travel freely through space. This event left an imprint still observable today: the cosmic microwave background radiation, a faint glow pervading all corners of the cosmos, and a snapshot of the universe at this early stage. But between recombination and the dawn of the first stars lies a vast stretch of time known as the Cosmic Dark Ages. During this era, the universe was filled with neutral hydrogen gas, cold and diffuse, with no sources of light or heat to break the solitude. There were no galaxies, no stars, no planets, just vast expanses of darkness stretching in every direction. It was a quiet interlude in cosmic history, but one that was crucial because it allowed gravity to begin its slow work, pulling matter together to seed the formation of stars and galaxies. Gravity, although weak on small scales, was the architect of the universe's large-scale structure. Minute variations in the density of matter, originating from quantum fluctuations during the earliest moments of the Big Bang, began to grow under gravity's persistent pull. Over millions of years, these small irregularities in the primordial matter coalesced into denser and denser regions, eventually forming the first cosmic structures. Understanding the vastness of deep time helps us appreciate just how patient and gradual the universe's evolution was. From one microsecond after the Big Bang to the first flickers of starlight, over hundreds of millions of years passed. These immense durations challenge our everyday notions of time and sequence, but are essential for the complex processes that allow matter to evolve from simple particles into atoms, molecules, stars, and eventually planets. Today, when we look into space with powerful telescopes peering billions of light years away, we are essentially looking back in time. Each photon of light carries a message from a distant epoch, providing clues to the universe's earliest chapters. Through these observations, combined with sophisticated computer simulations and theoretical models, scientists piece together the saga of cosmic evolution. This narrative is not simply academic. It touches upon our deeper questions. Where do we come from? How did the environments that would eventually give rise to life form? To approach the question of whether planets appeared before galaxies, we must first immerse ourselves in this profound backdrop, the deep, ancient time of the early universe, carving it into distinct epochs marked by fundamental physical processes and transformations. As we unfold this grand saga, we will venture next into defining exactly what we mean by first planets and first galaxies. By grounding ourselves in careful definitions, we can navigate the cosmic timeline with clarity, setting the stage for understanding the origins, conditions, and timelines of these celestial objects. Thus, with a sense of awe and curiosity, let us embark on this long journey through time, tracing the steps from the universe's fiery inception to the complex dance of matter that would, eons later, bring forth the very worlds we seek to comprehend. As we transition from contemplating the vast, silent expanses of the early universe's deep time, it becomes essential to clarify precisely what we mean when we speak of the first planets and first galaxies. These terms may seem straightforward at first glance, but as we delve into cosmic history, their definitions reveal layers of complexity that demand careful consideration. Establishing clear definitions is not merely an academic exercise. It is the foundation upon which we will build a coherent understanding of the universe's formative epochs and the sequence of events leading to the emergence of complex structures. The challenge begins with the word first itself. In daily language, first suggests a singular point in time, an absolute beginning. However, in cosmic terms, first often signifies a range or an epoch rather than a moment. This is because the processes that form planets and galaxies do not happen instantaneously or universally at once. Instead, they unfold gradually across vast regions of space and time, with some structures appearing earlier than others due to varying local conditions. To explore the meaning of first for galaxies and planets, let's start with galaxies, which are among the largest gravitationally bound structures in the universe. Galaxies vary enormously in size, shape, and composition, from sprawling spiral galaxies like our Milky Way to small, dim dwarf galaxies, and even irregular collections of stars and gas. When astronomers discuss the first galaxies, they generally refer to the initial gravitationally bound aggregations of stars and interstellar material large enough to be considered galaxies, which likely formed a few 100 million years after the Big Bang. These early galaxies can be thought of as embryonic structures, often smaller and less massive than typical galaxies in the present epoch. They are commonly called primordial or proto-galaxies, composed primarily of the first generations of stars, the so-called population 3 stars, which were massive and metal-free, consisting only of hydrogen and helium, the lightest and most abundant elements created in the aftermath of the Big Bang. These first galaxies offered the deep potential wells to accumulate gas and eventually foster the formation of successive generations of stars, introducing heavier elements into the interstellar medium. But what about the first planets? Here, the waters become murkier due to the particular requirements for planet formation as we understand it. Planets form through a process called accretion, where dust and gas orbiting young stars collide and stick together, gradually building up into larger bodies within a protoplanetary disk. However, terrestrial planets, planets with solid, rocky surfaces, and even gas giants require materials heavier than hydrogen and helium, what astrophysicists refer to as metals, meaning all elements heavier than helium. The first stars, being devoid of metals, initially created an environment with a scarcity of these heavier elements. It took successive generations of star formation and supernova explosions, powerful stellar deaths that scatter newly synthesized elements into space, to enrich the cosmos with the building blocks necessary for planet formation. Thus, the emergence of the first planets, at least those akin to what we find in our solar system, had to await this metallization of the interstellar medium. In defining the first planets, we must also consider different classifications. Are we envisioning any gravitationally bound object orbiting a star, regardless of its size or composition? Or are we referring specifically to Earth-like rocky planets that could potentially harbor life? And what about rogue planets? Planets not gravitationally tied to any star, drifting alone in interstellar space. These questions influence how we frame the timeline of planetary formation. From a strict astrophysical standpoint, the first planets could include any substellar bodies massive enough to clear their orbits and formed from accumulated material, even if they formed under unusual or inhospitable conditions. However, from a contextual perspective focused on habitability and complexity, we tend to emphasize planets formed in metal-enriched environments within mature galactic systems. A further complication arises when considering the formation of smaller cosmic structures like mini-halos, small congregations of dark matter and gas that may have concentrated prior to or alongside the earliest galaxies. Could these small halos have formed stars, and by extension planets, earlier than the large-scale galaxies? If so, such protostellar and protoplanetary systems might challenge the traditional galaxy-first sequence. Therefore, when we reflect on first galaxies, we refer broadly to the earliest self-gravitating stellar systems of sufficient mass and complexity to be identified as galaxies, which formed hundreds of millions of years after the Big Bang. These structures laid the foundation for ongoing cosmic evolution, enabling the processes that led to the formation of metals and subsequent generations of stars and planets. Conversely, first planets are best understood as the earliest formed planetary bodies within environments that contained sufficient heavy elements to coagulate solid material. These planets likely appeared later than the very first stars and galaxies, emerging only after the universe's cosmic chemical enrichment had reached a threshold conducive to planet formation. Yet, the distinction is not absolute. The timeline and definitions interweave and hinge on the very processes of star formation, metal enrichment, and the behavior of early cosmic structures. This nuanced understanding forms a critical bridge to exploring the cosmological timeline of the universe, from the Big Bang to the epoch of the first atoms, stars, and galaxies, where we will begin to trace the detailed sequence illuminating when and how planets and galaxies appeared relative to each other. Having clarified these foundational terms, we can venture with greater clarity and precision into the unfolding story of the universe's earliest epochs, setting the foundation for understanding the remarkable journey from simple particles to the complex cosmic tapestry embroidered with galaxies and planets alike. To grasp the unfolding drama of the universe's early epochs, we must map the timeline from the Big Bang itself through to the formation of the very first atoms. This cosmological timeline offers a detailed portrait of events that sculpted the universe from a hot, dense plasma into the vast expanse filled with matter capable of forming stars, galaxies, and eventually planets. The Big Bang, occurring approximately 13.8 billion years ago, marks the inception of all space, time, matter, and energy. It was not an explosion in space, but rather an expansion of space itself from an extremely hot and dense initial state. The immediate aftermath was a universe too energetic and chaotic to harbor familiar matter as we know it. Instead, it was a seething quark-gluon plasma, where fundamental particles interacted in a high-energy melee. During the first fractions of a second, what physicists call the Planck epoch and subsequent inflationary epoch, the universe expanded astonishingly rapidly, smoothing out large-scale irregularities and laying the foundation for the large-scale structure we observe today. Quantum fluctuations in this epoch sowed the tiny density variations that gravity would later amplify into galaxies and clusters. Within just a few minutes, the universe cooled enough to allow the first nucleosynthesis, the formation of light nuclei. This period, spanning roughly from 10 seconds to a few minutes after the Big Bang, is known as Big Bang nucleosynthesis. Here, protons and neutrons combined to form the first atomic nuclei, predominantly hydrogen, about 75% by mass, and helium-4, about 25%, along with trace amounts of deuterium, helium-3, and lithium-7. These elements comprise the primordial chemical inventory of the cosmos. However, the temperature remained prohibitively high, on the order of billions of degrees, for electrons to combine with nuclei. The universe was a hot plasma of nuclei, free electrons, photons, and dark matter particles all interacting frequently. Photons constantly scattered off the free electrons, rendering the universe opaque, much like the dense fog conceals distant objects on a misty day. For nearly 380,000 years after the Big Bang, this plasma epoch persisted. During this time, the universe expanded and cooled to around 3,000 Kelvin. At this threshold, electrons slowed down enough to combine with nuclei, primarily hydrogen and helium nuclei, to form neutral atoms. This pivotal moment, called recombination, transformed the universe. Recombination marked the transition from an opaque plasma to a transparent cosmos where photons could travel freely. The light released during this era forms what we now observe as the cosmic microwave background radiation, CMB, a faint, nearly uniform glow seen in every direction in our sky. The CMB serves as an invaluable window into the infant universe, encoding the initial conditions that led to all subsequent structure formation. Shortly after recombination, the universe entered the so-called cosmic dark ages, a period where neutral hydrogen filled space, yet no luminous sources had ignited. During this time, matter continued to coalesce under gravity, but the absence of stars meant that the cosmos was shrouded in darkness beyond the faint afterglow of the CMB. Tracing this timeline allows us to contextualize the emergence of complexity, from free elementary particles to nuclei to atoms capable of cooling and clumping effectively. It is within these succeeding epochs that gravity began to pull atoms together into ever denser regions, setting the stage for the ignition of the first stars, the cosmic engines that would manufacture heavier elements and eventually seed planetary systems. To break down the timeline further, in the first millionths of a second, the universe underwent rapid inflation, growing exponentially. Within the first 3 minutes, Big Bang nucleosynthesis created a primordial cocktail of light elements. For the next 370,000 years, the universe remained ionized, with photons trapped in a dense plasma. Around 370,000 years post-Big Bang, recombination allowed atoms to form, and the universe became transparent. Following recombination, the cosmic dark ages persisted before the formation of the first luminous objects. This chronological scaffolding clarifies how time and physical processes work hand in hand to seed the universe with the fundamental ingredients necessary for the complex structures to come. It teaches us that the first atoms, simple yet stable structures, were indispensable to the cosmic evolution that followed. Thus, from the primordial high-energy fireball of quarks and gluons, through a progressive cooling and particle formation, the stage was set for the universe's first objects. These were not stars or planets yet, but atoms, the fundamental building blocks from which all matter as we understand it derives. Understanding this timeline of the emergence of the first atoms is crucial as a baseline for examining the subsequent epochs, where the darkness of the universe begins to be pierced by light, and structures, galaxies, and eventually planets take shape. As we continue to journey deeper into the early universe's timeline, we arrive at a pivotal epoch known as the Era of Recombination, a critical phase that fundamentally transformed the state of the cosmos and set the conditions necessary for the emergence of structure, complexity, and, ultimately, the galaxies and planets we seek to understand. To understand the significance of recombination, it's important to recall the state of the universe immediately prior to this era. For nearly 370,000 years following the Big Bang, the universe was an extremely hot, dense plasma consisting of a soup of ionized particles, free protons, electrons, helium nuclei, alpha particles, photons, and a bath of neutrinos and dark matter. In this plasma, the rampant energy caused photons, particles of light, to scatter continuously off free electrons, making the universe opaque, effectively like a dense fog where light could not travel far without being absorbed or scattered. Recombination derives its name from the process whereby free electrons and protons combined, or more precisely, the recombination of electrons and nuclei to form neutral atoms. However, this term can be somewhat misleading since, prior to this epoch, electrons and nuclei had never been bound. This was the first epoch of atom formation. Yet historically, the term recombination stuck. As the universe expanded, its temperature steadily declined from billions of degrees Kelvin down to approximately 3,000 Kelvin. At this temperature, conditions became favorable for electrons to slow sufficiently to be captured by positively charged nuclei, forming the first stable hydrogen and helium atoms. This was a delicate balance because, at higher temperatures, photons were energetic enough to immediately ionize any formed atoms, breaking electrons free again. The recombination process was not instantaneous, but occurred over tens of thousands of years. The capturing of electrons into atomic orbitals predominantly involved hydrogen, the most abundant element, accounting for about 75% of the baryonic matter, with helium contributing about 25%. These newly formed neutral atoms no longer scattered photons as vigorously as free electrons did, causing the universe to transition from opaque to transparent. This transparency was revolutionary. Photons, which had been trapped and bounced around inside the plasma, were now free to travel vast distances uninterrupted. This release of free-streaming photons gave rise to the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang that permeates the universe today. Discovered inadvertently in 1965 by Arno Penzias and Robert Wilson, the CMB provides a snapshot of the universe at the moment recombination ended. Its almost uniform temperature of about 2.7 Kelvin, with tiny fluctuations of only a few parts in 100,000, encodes invaluable information about the distribution of matter and energy at that time, laying the groundwork for understanding how cosmic structures formed. The transition during recombination also conferred the universe's identity as a reservoir of neutral hydrogen gas, which now filled the cosmos expansively and homogeneously. This neutral hydrogen was critical because it could cool and collapse under gravitational attraction much more effectively than the previous ionized plasma. Its presence allowed the formation of dense clouds of gas, the precursors to the first stars. The recombination era is also distinguished by the concept of the surface of last scattering. This phrase describes the spherical shell around us, representing the layer of space from which the CMB photons last scattered before traveling freely to our telescopes. By studying this surface, astronomers and cosmologists reconstruct the early density fluctuations that would eventually evolve into galaxies and clusters, an extraordinary scientific achievement bridging theory and observation. While hydrogen was the most prevalent element during and after recombination, helium and trace light elements, synthesized during Big Bang nucleosynthesis, were also present predominantly as neutral atoms. Of note, the formation of neutral helium proceeded somewhat differently due to its higher ionization energy. But by the end of the recombination epoch, helium-2 combined into neutral atoms. Recombination also set the stage for the subsequent era known as the Cosmic Dark Ages, a period during which the universe, though neutral and transparent, lacked sources of light such as stars or galaxies. Yet this quietude belied a dynamic underlying dance. Gravity was steadily working on the density fluctuations revealed in the CMB, pulling matter together and initiating the slow but inexorable formation of cosmic structures. Another fascinating aspect to this era is that despite the formation of neutral atoms, the universe was not chemically rich. The entire cosmic gas was composed almost exclusively of hydrogen and helium, with virtually no heavy elements, referred to as metals in astrophysical terms. This scarcity of metals had profound implications for how gas cooled and how the first stars and galaxies would emerge. In summary, the era of recombination stands as a monumental turning point in cosmic history, where the universe shifted from an opaque, hot ionized plasma to a transparent, cool, and neutral hydrogen-filled expanse. It allowed photons to journey freely, giving us the cosmic microwave background that illuminates the infant universe. More importantly, the neutral hydrogen born in this epoch became the reservoir from which gravity sculpted the first stars and galaxies. This set in motion the cosmic evolution's next chapter, the end of the cosmic dark ages and the eventual formation of luminous bodies, the very beacons that eventually led to the formation of planets. In our next exploration, we will delve into the cosmic dark ages themselves, that vast epoch of primordial darkness where the cosmos was filled with neutral hydrogen and helium, left to quietly evolve until the first stars ignited. Understanding what filled the universe before stars shone is key to piecing together the puzzle of when and where the first galaxies and planets took shape. Following the transformative and luminous era of recombination, the universe embarked on a long, shadowed epoch, stretching across hundreds of millions of years, known as the Cosmic Dark Ages. This period occupies a pivotal position in cosmic history. It is the quiet, profound interlude between the birth of the first atoms and the formation of the first luminous objects, such as stars and galaxies. To fully appreciate the timeline and processes leading to these first lights, we must delve into what the universe was like during these enigmatic dark ages. A universe devoid of starlight, filled predominantly with a vast neutral hydrogen fog. At the conclusion of recombination, roughly 370,000 years after the Big Bang, the universe had cooled sufficiently for electrons and protons to combine into stable, neutral atoms, primarily hydrogen and helium. This transition from an opaque plasma to a transparent cosmos allowed photons to stream freely for the first time, a milestone immortalized in the cosmic microwave background radiation. Yet, even as light could now traverse cosmic distances unimpeded, sources producing new light remained absent. The cosmic dark ages thus began, a time when the universe was dark, silent, and still, bathed only in the faint glow of the cooling CMB. The cosmic dark ages were remarkably uniform in composition. Nearly all baryonic matter was neutral hydrogen gas, accompanied by a lesser amount of helium. These gases filled the cosmos nearly homogeneously, with only minute density fluctuations, small ripples in the fabric of matter left over from the universe's earliest quantum fluctuations. No stars, no galaxies, and no planets had yet formed to produce starlight or other electromagnetic signals detectable across great distances. Without sources of ionizing radiation, neutral hydrogen dominated the cosmic landscape. This simple atomic gas was both the canvas and the raw material for all later cosmic structures. It was, however, an incredibly inhospitable environment. Temperatures, while cooler than during recombination, were still on the order of a few tens of Kelvin. This cold gas was diffuse and under low pressure, and the universe lacked complex molecules or dust grains that, today, play a fundamental role in star and planet formation. Despite the apparent stillness, gravity was quietly and relentlessly influencing the cosmic expanse. Small overdensities, regions where matter was just slightly denser than average, began to attract neighboring particles, pulling in hydrogen gas and dark matter alike. Over millions of years, these slight irregularities grew in size and density, gradually developing into the earliest potential sites for star formation. Gravity, thus, was sowing the seeds of complexity even in this obscure and murky era. The absence of stars and their radiation meant no light sculpted the environment during the Dark Ages, but the lack of ionizing photons also had implications for chemistry and cooling. Without ultraviolet light to ionize gas or catalyze complex molecules, the primordial hydrogen remained largely atomic and inert. Unlike gas clouds in today's universe, where molecular hydrogen and heavier elements help cool gas to fuel star formation, the Dark Ages hydrogen gas had limited cooling pathways. This limitation affected how and when the first stars could finally ignite. Intriguingly, the end of the Dark Ages did not arrive suddenly, but marked the crescendo of the universe's slow march toward complexity. Eventually, the densest pockets of hydrogen and dark matter collapsed under their own gravity in what cosmologists call minihalos, small gravitational wells with masses large enough to collect and compress gas to conditions ripe for nuclear fusion ignition. It was within these mini-halos, roughly 100 million to 200 million years after the Big Bang, that the first stars, population 3 stars, would blaze to life, breaking the cosmic silence and heralding a new epoch. In summary, the cosmic Dark Ages represent a vast temporal frontier where the universe was filled with diffuse, neutral hydrogen and helium gas, silent and dark, unblemished by the radiance of stars or galaxies. It was a delicate balance of forces, matter coalescing under gravity, but star formation delayed by the absence of metals and molecules essential for efficient cooling. Without this era, the cosmos would lack the structure necessary to seed galaxies and planets. Next, we will explore the profound influence of gravity during this era, the unseen architect sculpting the fabric of the universe from quantum fluctuations toward the first star-forming regions. Understanding how gravity operated during the Dark Ages reveals how the universe transitioned from darkness to the first glimmers of starlight, moving closer to the birth of galaxies and, eventually, planets. In the silent vastness of the cosmic Dark Ages, when the universe was filled predominantly with neutral hydrogen and helium gas, an invisible but powerful force was patiently shaping the future. This force was gravity, the ever-present architect of cosmic structure, secretly at work turning the near-uniform matter of the early universe into the intricate tapestry of galaxies, stars, and ultimately planets. To understand the origins of the first cosmic structures, we need to explore the subtle yet profound role gravity played, starting from minuscule quantum fluctuations in the fabric of space-time. At the heart of this process lies the extraordinary fact that the universe was not perfectly uniform after the Big Bang. Instead, it bore tiny irregularities in density, known as perturbations or fluctuations. These were the seeds of all cosmic structure. But where did they come from? The source of these initial fluctuations can be traced back to the realm of quantum mechanics, in particular to phenomena occurring during the inflationary epoch, an unimaginably brief moment almost immediately after the Big Bang, when the universe expanded exponentially. Inflation not only stretched space itself, but also magnified minute quantum uncertainties into macroscopic density fluctuations, imprinting subtle variations in matter and energy density throughout the cosmos. These variations are incredibly faint, only about 1 part in 100,000 times, but they carried the blueprint for the vast cosmic web we observe today. Once inflation ended, the universe entered a more gradual expansion phase, cooling and allowing matter to start its gravitational dance. In regions where these small fluctuations represented slightly higher densities, gravity began to exert its influence. Remember, gravity is an attractive force. Denser regions pulled in surrounding matter, growing more massive and denser. Yet, in the early universe, this process was not straightforward. The cosmic gas was hot and expanding, and radiation pressure from photons pushed outward, counteracting gravitational contraction in many areas. That said, the fluctuations provided the necessary initial conditions for gravity to slowly gain ground. Over time, the densest clumps overcame the opposing forces, halting their expansion and starting to collapse. Dark matter played a crucial and enigmatic role during this epoch. Unlike ordinary matter, dark matter does not interact electromagnetically. It neither emits, absorbs, nor scatters light. This characteristic allowed it to begin collapsing and clustering earlier and more efficiently, unimpeded by radiation pressure. Cosmologists believe that dark matter formed the gravitational scaffolding, the cosmic web, upon which ordinary matter later accumulated. These dark matter concentrations, known as halos, provided the gravitational wells that drew in neutral hydrogen and helium gas. As gas collected in these halos, it began cooling and condensing, laying the groundwork for the formation of the first stars. However, cooling was not trivial, given the primordial chemical simplicity of the universe. Without heavier elements, metals, that facilitate efficient gas cooling today, the proto-structures relied heavily on molecular hydrogen, an inefficient coolant, to shed heat and continue collapsing. During this slow buildup, the dense clumps within dark matter halos grew in size and mass. Mini-halos, with masses around 1,000,000 times that of our Sun, represented the first potential stellar nurseries. Within many of these dense regions, fragmentation further concentrated gas, increasing densities enough to ignite nuclear fusion and birth the first stars. The dynamical process of hierarchical structure formation, where small structures merged and accreted material to form larger ones, was central. Small mini-halos merged into more massive halos, which in turn formed the embryonic galaxies. This bottom-up growth contrasts with older theories positing that massive galaxies formed in one grand collapse. Gravity's work across these epochs is a tale of patience and interplay among matter types, radiation, and cosmic expansion. It translated microscopic fluctuations into macroscopic architecture, the stars, galaxies, and eventually planets that dot our night sky. In the grand cosmic timeline, gravity's nurturing of these fluctuations from mere quantum jitters to the majestic first structures is central to understanding the universe's evolutionary narrative. The initial steps of star formation within these nascent halos heralded a monumental cosmic transformation, paving the way for the chemical enrichment necessary for planet formation. Our next chapter will delve into the fascinating story of the first generation of stars, the population 3 stars, those unique, massive, metal-free pioneers that not only altered the universe's chemistry, but also initiated the processes essential for the birth of galaxies and planets. These stars were the seeds of cosmic change, forged by gravity's work on those primordial fluctuations we have just explored. As we progress from the gentle cobbling of matter into the first dense regions in the early universe, we now arrive at a defining milestone in cosmic history: the rise of the enigmatic population 3 stars. These were the universe's very first generation of stars, unique celestial beacons that carried monumental significance as the seeds of cosmic change and bearers of the first heavy elements or metals beyond the primordial hydrogen and helium. Understanding these primordial stars is crucial, as they played a transformative role in shaping the universe and enabling subsequent generations of stars, galaxies, and ultimately the planets we seek to understand. Population 3 stars formed within the earliest mini-halos, gravitationally bound clumps of dark matter and gas, about 100 to 400 million years after the Big Bang, during the closing chapters of the cosmic Dark Ages. Unlike stars that formed much later, population 3 stars were composed almost exclusively of hydrogen and helium, the simplest and most abundant elements generated during Big Bang nucleosynthesis. They contained virtually no heavier elements, metals in astronomical parlance, which profoundly influenced their formation and properties. This lack of metals meant that the gas from which these stars formed had limited cooling mechanisms. In today's universe, metals and dust grains play an indispensable role in cooling gas clouds, allowing them to fragment into smaller clumps and form low-mass stars like our Sun. Without metals or dust, the primordial hydrogen gas could only cool inefficiently, primarily through molecular hydrogen, which is far less effective. As a result, population 3 stars were theorized to be extraordinarily massive compared to most stars we observe today. Contemporary models estimate their masses ranging anywhere from tens to hundreds of times the mass of the Sun, possibly even reaching up to 1,000 solar masses in some cases. Their immense mass led to an immensely high core pressure and temperature, affecting very rapid nuclear fusion and short-lived lifetimes, typically a few million years, or even less. By contrast, smaller stars like our Sun burn their fuel over billions of years. The extraordinary mass and metal-free composition of population 3 stars meant they emitted intense ultraviolet radiation, capable of ionizing surrounding hydrogen gas. This radiation altered the local environment dramatically, initiating the process known as cosmic ionization, where the neutral hydrogen filling the universe became ionized again, transforming the cosmos and allowing light to propagate freely. But perhaps the most pivotal role of these first stars was their contribution to cosmic chemical enrichment. Their lives ended violent, often in spectacular supernova explosions, catastrophic outbursts that dispersed the heavy elements forged in their cores into the surrounding interstellar medium. This process seeded the early universe with metals essential for the formation of later generations of stars, population 2 and population 1, and for the complex chemistry necessary for planetary formation, population 3. Supernovae were powerful agents of change. The metals they dispersed not only enhanced the cooling ability of gas clouds, but also influenced the structure formation at multiple scales. They transformed the universe's chemical landscape, enabling gas clouds to fragment into smaller masses and paving the way for the emergence of lower-mass stars and planetary systems. Detecting population 3 stars directly remains a significant challenge for astronomers because they existed so far back in time and may have all perished early on. However, their legacy is imprinted in the chemical abundances of ancient stars that followed and in the rionization history of the universe. The study of extremely metal-poor stars in our galaxy and distant observations of early galaxies offer indirect but invaluable clues about these primordial stars. The discovery and understanding of population 3 stars have required a combination of theoretical modeling, computer simulations, and interpretations of observational data, as no direct observations of these stars have yet been confirmed. Their existence remains one of the most active research areas in cosmology, connecting the physics of the very small, nuclear reactions in stars, with the very large, the large-scale structure and evolution of the universe. Thus, population 3 stars were not only the first sources of light to pierce the cosmic darkness, but also the architects of chemical complexity, the celestial forges that made all elements beyond hydrogen and helium possible. Their formation, life cycles, and explosive deaths seeded the universe with the building blocks for all subsequent generations of stars, galaxies, and, critically for our inquiry, the raw materials necessary for planet formation. With this profound transformation in mind, our journey now moves toward exploring how stars create these necessary elements for planets, delineating the cosmic alchemy that converts the simple primordial universe into the richly diverse cosmos capable of hosting worlds like our own. In order to truly grasp how planets could ever form in the universe, we must understand the stellar processes that create the elements essential for their formation. The universe, in its earliest epochs, was composed almost exclusively of hydrogen and helium, simple, light atoms synthesized in the first minutes after the Big Bang. Yet, these elements alone cannot produce the diverse array of planets we observe today, especially rocky planets rich in metals like iron, silicon, oxygen, and carbon. For these heavier elements, it is the life cycle of stars that acts as an extraordinary cosmic foundry, forging and dispersing the raw materials of planets throughout space. Stars are essentially massive, self-gravitating spheres of hot plasma, where intense pressure and temperature in their cores ignite nuclear fusion, the process of combining lighter nuclei into heavier ones, releasing enormous amounts of energy that sustains the star over millions to billions of years. This fusion process is not only the star's power source, but also the primary driver of chemical complexity in the universe. Initially, stars fuse hydrogen nuclei into helium through a series of reactions called the proton-proton chain, or, in more massive stars, the carbon-nitrogen-oxygen (CNO) cycle. While helium is the simplest of the heavier elements, stars advance beyond this basic stage by continuing to fuse helium into even more massive nuclei, such as carbon and oxygen, in their later evolutionary phases. The stellar interior acts like an onion with layered shells, each fusing progressively heavier elements as the star ages and its core contracts and heats. After helium, stars fuse carbon, neon, oxygen, and silicon progressively in their cores, creating a stratified structure where each layer is burning different fuel. This process moves toward producing elements up to iron, which is notable because iron fusion does not release energy, but instead requires energy input, marking an end to the star's life support mechanism. Elements heavier than iron, like gold, uranium, and many others, are predominantly created through rapid neutron capture processes, the R process, during the dramatic, explosive deaths of massive stars known as supernovae, or during neutron star mergers. These cataclysmic events provide the energetic environments needed to forge elements beyond iron, which cannot be produced through normal stellar fusion. Once the star reaches the end of its life, Its death triggers a dispersal of these freshly forged elements into space. Massive stars conclude their lives in supernova explosions, ejecting vast quantities of metals into the surrounding interstellar medium. Lower mass stars, like our Sun, gently shed their outer layers as planetary nebulae, enriching space with lighter elements such as carbon and nitrogen. These processes gradually increase the metallicity of the gas clouds, from which new stars and planets eventually form. This cyclical enrichment is crucial. Without it, the ingredients for rocky planets and complex chemistry simply do not exist. The first generation of stars, the metal-free population 3 stars, lived fast and died young, essentially seeding the cosmos with metals through their supernova, creating the chemical diversity necessary for later generations of stars and their planetary systems. The presence of metals and dust grains in star-forming regions facilitates cooling of the gas, enabling clouds to collapse further and fragment into small, dense cores, essential precursors for the formation of both stars and accompanying protoplanetary disks. Within these disks, the heavy elements condense into solids ranging from tiny dust grains to planetesimals, the building blocks of planets. In summary, stars are not only luminous beacons lighting the cosmos, but indispensable alchemists, transmuting primordial hydrogen and helium into the rich elemental library that makes planets, and by extension, life as we know it, possible. This stellar alchemy unfolds over cosmic timescales through successive generations of stars, each contributing to the evolving tapestry of elements that seeds the formation of worlds. With this understanding in place, we are poised to examine the life and death cycles of the first stars themselves and how these violent cosmic events have shaped the path toward the formation of galaxies and planets that followed. As we delve deeper into the cosmic history of the universe, the life cycles of the first stars, population 3 stars, stand out as a dramatic and transformative chapter. These early luminaries, forged from pristine hydrogen and helium, underwent rapid and tumultuous lives whose violent deaths sowed the seeds for all future cosmic complexity, including galaxies and planets. Understanding their stellar evolution and explosive demise is critical to recognizing how the universe transitioned from darkness and simplicity to richness and structure. Population 3 stars are theorized to have been extraordinarily massive, often exceeding tens or even hundreds of times the mass of our Sun. This immense mass drove their rapid consumption of nuclear fuel, leading to brief lifespans of only a few million years, astonishingly short by cosmic standards. During their main sequence phase, these massive stars fused hydrogen into helium in their cores, radiating intense ultraviolet light that began altering the chemical and thermal state of their surroundings. As these stars exhausted their hydrogen fuel, they passed through successive stages of fusion, forming heavier elements in layered shells around their cores, helium, carbon, oxygen, and so forth, until they produced iron. Iron, unlike lighter elements, does not yield energy through fusion. The buildup of an iron core signaled the impending death of these stars, as the core could no longer sustain the outward pressure balancing gravity. When the iron core reached a critical mass, it collapsed catastrophically under its own gravity, triggering a core collapse supernova, one of the most energetic events in the universe. This explosion expelled vast amounts of stellar material at tremendous velocities into the surrounding interstellar medium. These supernovae were not only luminous explosions visible across cosmic distances, but also the means by which the universe was enriched with the first heavy elements, or metals. The metals synthesized in the cores of population 3 stars, along with those formed during the supernova nucleosynthesis process itself, were crucial. Elements such as carbon, oxygen, silicon, iron, and others were scattered into space, contaminating the previously metal-free hydrogen and helium gas. This enrichment dramatically altered the cooling properties of interstellar gas, allowing subsequent generations of stars, population 2 and later population 1, to form with lower masses and longer lifetimes. Some population 3 stars, particularly the most massive ones, may have ended their lives as pair instability supernovae, a theoretical type of explosion so powerful that it completely disrupts the star without leaving behind a compact remnant like a neutron star or black hole. These supernovae would have released copious heavy elements into space, giving rise to the chemically enriched environments necessary for planet formation. Other population 3 stars likely collapsed directly into black holes, either quietly or with less energetic supernovae, leaving behind dark remnants that may have served as seeds for the supermassive black holes observed at the centers of modern galaxies. The relatively short lifespans and explosive deaths of population 3 stars thus played a pivotal role in shaping the chemical and structural evolution of the universe. Their supernovae provided the metals necessary for the formation of dust, molecules, and the complex chemistry required for the birth of planets. Without these processes, the universe would remain a vast expanse of sterile hydrogen and helium gas. Interestingly, while direct observations of population 3 stars remain elusive due to their ancient and transient nature, astronomers study their legacy by examining the chemical abundances found in extremely metal-poor stars in our own galaxy and distant ancient galaxies. These stellar fossils carry the signatures of early supernova enrichment, offering indirect evidence of the first star's properties and behaviors. In sum, the life and death of the first stars were a cosmic fireworks display that seeded the universe with the elemental diversity foundational to all subsequent cosmic structures. Their fiery demise initiated the chemical evolution that set the stage for galaxy formation and, crucially, for the formation of planets, rocky worlds composed of the very elements their cores forged. With this understanding in hand, we are prepared to explore the assembly of these first galaxies themselves, tracing how the remnants of the first stars and their chemical legacy coalesced into the earliest large-scale cosmic structures. The story of the first galaxies is one of cosmic complexity, a tale woven from the threads of gravity, chemistry, and time. After the era when the first stars ignited, lighting up cosmic darkness, these luminous islands began gathering into increasingly massive structures. The assembly of the first galaxies marks a key phase in the evolution of the universe, representing the transition from isolated stars to vast, gravitationally bound systems composed of billions of stars, gas, dust, and dark matter. Today, our quest to understand this formative chapter is guided by clues drawn from the cutting edge of observational cosmology. Galaxies are colossal systems, held together by gravity, composed predominantly of dark matter enveloping gas and stars. The assembly of the earliest galaxies occurred gradually as dark matter halos merged and accreted surrounding gas, providing environments where star formation proceeded more efficiently. The first galaxies were likely small, irregular, and less luminous than many galaxies observed in the nearby universe. They served as the building blocks of the complex hierarchical structure of cosmic evolution. Observational cosmology, advanced through telescopes spanning the electromagnetic spectrum, offers windows into these distant and ancient objects. The farther away we look, the farther back in time we see, because light takes time to travel across the universe. Observing high redshift galaxies, galaxies whose light has been stretched to longer wavelengths by cosmic expansion, enables us to glimpse them as they were in the early universe. One key tool in this endeavor is the Hubble Space Telescope, which has been instrumental in discovering candidate galaxies formed less than 1 billion years after the Big Bang. The Hubble Ultra Deep Field image, for instance, reveals faint, distant galaxies whose light has traveled for more than 13 billion years. Their small size and irregular shapes fit the theoretical expectations for nascent galaxies still in the process of assembling. Spectroscopic observations provide additional vital information. By dispersing the light from these early galaxies into its constituent wavelengths, astronomers identify emission and absorption lines characteristic of hydrogen, helium, and heavier elements. The presence and intensity of these spectral features allow us to gauge star formation rates, metallicity, chemical enrichment, and gas dynamics within these primordial systems. Radio and sub-millimeter observations from facilities like the Atacama Large Millimeter Submillimeter Array, ALMA, further reveal the cold molecular gas and dust within these young galaxies, crucial components fueling star formation. These observations help us piece together how rapidly early galaxies formed stars and how they accumulated dust and metals expelled by previous generations of stars. More recently, the James Webb Space Telescope, JWST, with its unprecedented sensitivity and infrared capabilities, has begun unveiling even earlier galaxies. Detecting galaxies at redshifts greater than 10, meaning their light comes from less than 500 million years after the Big Bang, JWST allows astronomers to probe the structure, composition, and evolution of the universe at epochs hitherto inaccessible. The observed properties of the first galaxies align remarkably well with theoretical simulations, which predict that these objects were dominated by intense star-forming regions, rich in hot, young stars, but relatively poor in metals and dust compared to galaxies today. They also suggest rapid assembly through successive mergers and accretion of gas. However, many challenges remain. Distinguishing truly primordial galaxies from slightly more evolved systems requires precise measurements and cosmic variance. The fact that the universe's large-scale structure is not uniform everywhere complicates broad conclusions. Furthermore, early galaxies were likely enshrouded in neutral hydrogen, making them difficult to detect in certain wavelengths due to absorption. Yet, the convergence of observational data with cosmological simulations provides powerful support for our current understanding. The first galaxies grew from the gravitational collapse and merger of dark matter halos, enriched internally by star formation and externally by the feedback from supernovae and stellar winds. These first galaxies were the cosmic homes where metal-enriched gas began to accumulate, setting the stage for the formation of planetary systems in later epochs. Their assembly heralded a new complexity in the universe, structures capable of nurturing the chemistry and environments necessary for planets. As we look ahead, next-generation observatories promise to sharpen our view even further, enabling us to peer deeper into the cosmic dawn and uncover how the grand architecture of galaxies and the planets within them came to be. But to fully grasp the story, we must also turn to theoretical frameworks and simulations that reconstruct early galaxy formation, providing insights into the processes hidden beyond our telescope's reach. As we continue our journey into the earliest epochs of cosmic history, a fundamental challenge confronts astronomers: finding and studying ancient galaxies, the very first vibrant tapestries of stars and gas that emerged from the primordial universe. These earliest galaxies hold the keys to understanding the timeline of cosmic evolution and answering profound questions about the dawn of structure and ultimately planet formation. Today, our knowledge stems from cutting-edge observational campaigns that push the limits of telescopes and technology to peer back in time across billions of light years. The cornerstone of observational cosmology's search for ancient galaxies lies in examining high redshift objects. Redshift refers to the stretching of light's wavelength due to the universe's expansion. The higher the redshift, the further back in time and space the object lies. Observing galaxies at redshifts greater than 6 means seeing them as they were when the universe was under 1 billion years old, a critical window into the epoch of rayonization and the assembly of the first galaxies. Ground-based observatories with large apertures and advanced detectors, such as the Very Large Telescope, VLT, and the Keck Observatory, have contributed significantly to this quest. Using spectroscopic techniques, astronomers have pinpointed galaxies at redshifts approaching 10, corresponding to times less than 500 million years post-Big Bang. These observations reveal young galaxies characterized by intense bursts of star formation, relatively low metallicities, and modest masses. Space-based observatories have been particularly transformative in this field. The Hubble Space Telescope, HST, with its deep imaging capabilities, has played an essential role in detecting faint high-redshift galaxies. The Hubble Ultra Deep Field, HUDF, and subsequent campaigns pushed the detection of galaxies to redshifts beyond 8, unveiling a population of small, faint, and irregular galaxies that are likely among the universe's earliest. However, Hubble's sensitivity in near-infrared wavelengths, crucial to seeing these distant galaxies, has limitations. This gap is now being filled by the James Webb Space Telescope, JWST, whose highly sensitive infrared instruments have revolutionized the search for ancient galaxies. JWST's ability to detect even fainter and more distant galaxies has already led to the discovery of numerous candidates at redshifts above 10, corresponding to just a few 100 million years after the Big Bang. These observations provide several critical insights. First, the abundance of early galaxies suggests that galaxy formation began quite rapidly after the cosmic dark ages, consistent with theoretical predictions. Second, analyzing the light spectra from these galaxies reveals clues about their stellar populations, chemical enrichment, and star formation rates in the infant universe. Most show signs of ongoing vigorous star formation, but with metallicities much lower than those in later cosmic times, indicative of early generations dominated by massive stars. Further evidence comes from observations in other wavelengths, such as the Atacama Large Millimeter Point Submillimeter Array, ALMA, which probes the cold molecular gas and dust within early galaxies. These radio observations are vital for understanding the raw materials feeding star formation and grain formation, the building blocks of planet formation. Surprisingly, ALMA has detected dust and heavy elements in some of these young galaxies, indicating that chemical enrichment processes, driven by the first generations of stars, progressed quickly even at such high redshifts. In addition to direct galaxy observations, astronomers study the so-called Lyman alpha emitters and dropout galaxies identified through specific spectral signatures caused by hydrogen gas absorption. These techniques help isolate truly ancient galaxies from interlopers and construct a census of early cosmic structures. Despite the advances, challenges persist. The faintness and small angular sizes of these galaxies, cosmological surface brightness dimming, and intergalactic hydrogen absorption complicate observations. Cosmic variance also affects sample sizes, meaning that observing a limited patch of sky may not represent the average cosmic environment. Furthermore, distinguishing genuine primordial galaxies from evolved ones requires precise measurements and sophisticated modeling. In summary, the current observational evidence points to a rapidly evolving early universe where galaxies formed in earnest relatively soon after the Big Bang, serving as the cosmic crucibles for star formation and chemical enrichment. While direct detection of the very first galaxies remains at the forefront of observational cosmology, synergistic efforts across multiple facilities and wavelengths are steadily illuminating their properties and prevalence. Building on these observations, theorists and computational cosmologists use simulations and models to reconstruct the formation and evolution of these earliest structures, helping us bridge the gap between observation and understanding. This next step will shed light on the physical mechanisms governing early galaxy assembly and inform our comprehension of when and how planets might have first taken shape within them. In the quest to understand the universe's earliest galaxies, and, by extension, the conditions that led to the formation of the very first planets, astronomers and cosmologists rely heavily on simulations and theoretical models. Observing the infancy of the cosmos directly is fraught with difficulties. The immense distances, the faintness of primordial galaxies, and absorption by intergalactic hydrogen make direct detections challenging and data incomplete. To bridge this observational gap, theorists construct detailed simulations based on fundamental physical laws to reconstruct early galaxy formation and evolution. These computational simulations are monumental undertakings. They start from initial conditions derived from the cosmological parameters of the universe, such as matter density, dark energy, and the statistical properties of primordial density fluctuations, the very quantum seeds imprinted during cosmic inflation. Using these initial landscapes, simulations evolve matter and energy forward through time under gravity, hydrodynamics, and thermodynamics. One fundamental framework is the lambda cold dark matter, LCDM model, currently the prevailing cosmological model. It posits that most of the universe's matter is cold dark matter, which interacts gravitationally but not electromagnetically, guiding the formation of large-scale structures. In simulations, dark matter halos emerge first, providing gravitational wells into which baryonic matter, normal gas, can fall and cool to form stars and galaxies. The simulations integrate complex physical processes, including gas cooling, star formation, feedback from supernovae and active galactic nuclei, chemical enrichment, radiation transport, and the influence of cosmic expansion. Modeling feedback is especially challenging as energy and momentum input from massive stars' winds, radiation, and supernova explosions regulate subsequent star formation, preventing runaway collapse and affecting the galaxy's morphology. High-resolution simulations like Illustris, Eagle, Fire, and Renaissance have significantly advanced our understanding of early galaxy formation. These simulations are run on supercomputers due to the extreme computational demands, often requiring millions of CPU hours to evolve volumes of the universe with fine spatial and temporal detail. They predict that the first galaxies formed in halos with masses around 1 billion times that of the Sun. Initially, these systems were small, irregular, and dominated by bursts of star formation. Successive mergers and accretion events allowed them to grow in size and complexity, developing the structures, disks, spheroids, and bulges that typify mature galaxies. Simulations also provide insights into the interplay of metal enrichment and star formation. Metals synthesized in the first generations of massive stars change the cooling efficiency of interstellar gas, altering star formation modes and enabling the formation of lower-mass stars more similar to our Sun. This gradual chemical evolution is critical for planet formation, which depends on the presence of heavy elements. Radiation hydrodynamic simulations study how the intense ultraviolet light from early massive stars and black holes rionized the neutral hydrogen that filled the cosmos after recombination. This rionization epoch left signatures detectable in the cosmic microwave background and in the spectra of distant quasars, providing complementary observational constraints against which simulations are tested. Another crucial aspect involves simulating the formation and evolution of population 3 stars within primordial minihalos. These simulations probe how metal-free gas cools inefficiently, resulting in massive stars that quickly enrich their surroundings with metals, leading to population 2 star formation and the birth of the first galaxies. While the simulations steadily improve in physical fidelity and resolution, challenges remain. Many processes occur on scales below current computational resolution, requiring approximations known as subgrid models. Accurately modeling feedback mechanisms and star formation physics to match observations is an ongoing scientific endeavor. Nevertheless, simulations and models serve as indispensable tools, synthesizing the intricate astrophysical processes from fundamental physics to emergent cosmic structures. They provide virtual laboratories to test hypotheses, interpret observations, and predict properties of galaxies in the first billion years. These theoretical reconstructions help reveal timelines for when galaxies formed, how rapidly they grew, and when elements necessary for planet formation became prevalent. As we move forward, simulations will increasingly incorporate data from new observatories, like JWST and the Extremely Large Telescope, to refine our understanding of the first galaxies and their environments. This synergy between theory and observation culminates in a richer picture of the universe's early chapters, intimately tied to the origins of planets themselves. Armed with this theoretical foundation, we can now turn to the fundamental conditions that must be met within galaxies and their star systems for planets to arise, exploring what cosmic ingredients and environmental factors are indispensable for that next transformative step in cosmic evolution. As we venture deeper into the cosmic saga, focusing now on the birth of planets, it is essential to explore the fundamental conditions that must exist for planetary formation to occur. While stars ignite through the fusion of hydrogen and helium, planets emerge from more intricate circumstances, requiring a specific set of ingredients and environmental factors that transform diffuse cosmic matter into cohesive worlds. At its core, planet formation occurs within the circumstellar disks of gas and dust that encircle young stars, known as protoplanetary disks. These disks are cradles of planetary birth, where material coalesces through processes like accretion, collision, and condensation, but several prerequisites underpin this complex orchestration. First and foremost is the presence of heavy elements, or metals in astrophysical terms. Elements heavier than hydrogen and helium, including carbon, oxygen, silicon, iron, magnesium, and others. These elements are critical because they make up the solid grains and dust particles that serve as the building blocks of planets. Without metals, protoplanetary disks would be composed almost entirely of gaseous hydrogen and helium, which cannot easily clump into solid planetary cores. These metals arise from the nucleosynthesis in previous generations of stars, dispersed into the interstellar medium through processes such as supernovae and stellar winds. Hence, metal-enriched environments are a prerequisite for forming terrestrial, rocky planets and the cores of gas giants. This dependence introduces a cosmic timescale element. Planets can only form after the universe has been chemically enriched by multiple cycles of star formation and death. Next, the protoplanetary disk must possess sufficient mass and density. If the disk is too sparse, particles do not collide frequently enough to allow growth into larger bodies. Conversely, a very massive disk may promote rapid migration of formed planetesimals, potentially disrupting their orderly accretion into stable orbits. Temperature within the disk also plays a crucial role. Regions close to the star can be too hot for volatile compounds like water, methane, and ammonia to condense, limiting solid material primarily to refractory metals and silicates. Farther from the star, beyond the so-called snow lines, these volatile compounds solidify into ices, enhancing the solid mass available for planet building. This temperature gradient influences both the composition and type of planets that can form at different distances. The disk's lifetime is equally critical. Observations of young stellar objects suggest protoplanetary disks persist for only a few million to around 10 million years, a tight window for planet formation processes to unfold. If the disk dissipates too early, nascent planets may remain underdeveloped, or gas giants fail to gather massive envelopes. Turbulence and viscosity within the disk influence particle settling and collision rates, affecting how quickly solids coagulate. Magnetic fields and radiative effects can modulate these properties, adding further complexity to the environment. Another vital factor is the presence of dust grains and molecules. Dust serves as the seed material for planetesimals, but beyond mere presence, the size distribution, composition, and stickiness impact the efficiency of coagulation. Molecules such as molecular hydrogen, water vapor, carbon monoxide, and organic compounds contribute to disk chemistry and cooling, shaping conditions conducive to planet formation. Additionally, the host star's properties, mass, luminosity, and spectral type, govern the energy input to the disk, influencing temperature structures and photoevaporation rates. High-energy radiation from massive stars can erode disks quickly, potentially curtailing planet formation. Critically, planetary system formation also requires a relatively stable gravitational environment. Excessive dynamical perturbations, whether from nearby stars, intense stellar winds, or turbulent gas flows, can disrupt disk cohesion and the delicate accretion processes. Putting all these factors together, the conditions for planet formation crystallize as a delicate balance of chemical richness, sufficient material, suitable temperature regimes, stable environments, and adequate timescales. When this balance achieves harmony, microscopic dust grains aggregate into kilometer-sized planetesimals, which in turn collide and merge to form protoplanets, finally culminating in mature planets with diverse sizes and compositions. In the context of cosmic history, these requirements highlight why planets could not have formed immediately after the first stars appeared. The primordial universe was lacking in heavy elements, dust, and chemically complex molecules necessary for the process, delaying planetary formation until later cosmic epochs enriched by stellar evolution. As we proceed, we will examine whether planets could form around the universe's earliest stars, the population 3 stars, and delve deeper into the metallicity problem that ultimately dictates when and where planets became possible amid the burgeoning cosmos. Exploring the possibility of planets forming around population 3 stars plunges us into a frontier at the intersection of astrophysics and cosmic history, an exploration of whether planets could have emerged around the universe's very first metal-free stars. Population 3 stars, composed almost entirely of hydrogen and helium, represent a primordial stellar generation whose unique characteristics profoundly influence the question of planetary formation in the early cosmos. To begin, it is crucial to appreciate the defining attributes of population 3 stars. These stars formed from pristine gas clouds lacking any metals, elements heavier than helium, which are crucial to many astrophysical processes, including the cooling of gas and the formation of dust grains. Because metals facilitate gas fragmentation and cooling, their absence in primordial clouds meant that population 3 stars were extraordinarily massive, often exceeding tens or even hundreds of solar masses. Their immense mass and intense radiation environments profoundly shaped their surroundings. The extreme mass of population 3 stars directly impacts the likelihood and nature of planet formation around them. In modern star systems, planets generally form in protoplanetary disks, a rotationally supported disk of gas and dust particles encircling young stars, from which dust grains coagulate into planetesimals and eventually mature planets. Yet, for population 3 stars, the story is more complex. Firstly, the metal deficiency implies an absence of dust grains, the very seeds necessary for terrestrial planet formation. Metals condense into microscopic solid particles, enabling dust to exist in protoplanetary disks. Without these grains, the initial stages of planetesimal formation, dependent on aggregate dust grain growth, face significant obstacles. Thus, rocky planets, the building blocks of worlds like Earth, would be extremely unlikely around population 3 stars. Moreover, the intense ultraviolet and ionizing radiation emitted by massive population 3 stars would have a disruptive effect on any surrounding disk materials. Strong stellar winds and radiation pressure could rapidly disperse protoplanetary disks, truncating the timescales available for planet formation. With disks potentially short-lived and dynamically hostile, the intricate processes of dust grain coagulation and planetesimal assembly become further challenged. Additionally, the lifespan of population 3 stars is generally very brief, often just a few million years, due to their high masses and rapid nuclear fuel consumption. Given that planet formation, especially the assembly of large planetary cores or gas giants, operates on timescales of several million years or longer, the brevity of population 3 stars' lives constrains the window for any planets to form before the star ends its life. Another consideration is whether lower mass population 3 stars could have existed and provided more hospitable environments for planet formation. While theoretical studies and simulations largely suggest population 3 stars were predominantly massive, some recent models allow for the possibility of lower mass metal-free stars forming under specific conditions. These stars would have longer lifetimes and potentially could retain protoplanetary disks for sufficient durations, albeit still challenged by the metal paucity. However, to date, no convincing observational evidence of such low-mass population 3 stars has been found. Interestingly, some models propose that population 3 stars could have hosted gas giant planets formed from gravitational instabilities in massive metal-poor disks. Yet, such scenarios remain speculative and are subject to complex physical constraints, including disk stability and cooling efficiency in environments devoid of metals and dust. In the grand cosmic evolutionary framework, it is more plausible that the first planets formed around later generations of stars, dubbed population 2, which formed from gas clouds enriched by the metals dispersed in population 3 supernovae. This metal-enriched environment fostered the formation of dust and complex molecules essential for robust protoplanetary disk development. In summary, while nature often surprises us with unexpected outcomes, prevailing astrophysical understanding suggests that planet formation around population 3 stars was highly unlikely due to their mass, brief lifetimes, and metal-free composition. These earliest stars ignited the cosmic dawn and created the essential heavy elements through their explosive deaths, setting the stage for a later era when the cosmos became fertile ground for planet formation. This insight naturally leads us to examine more deeply the metallicity problem, the fundamental role heavy elements play in forming planets, and how the metal enrichment of the interstellar medium enabled the universe's progression from stars alone to star systems with accompanying planets. The quest to understand planetary formation inevitably leads us to confront a critical astrophysical challenge known as the metallicity problem. At its essence, this problem highlights the indispensable role that heavy elements, what astronomers collectively call metals, meaning all elements heavier than helium, play in allowing planets to form. To grasp why these metals are so vital, and when they first became available in sufficient quantities in the cosmos, we must examine both the nature of planetary formation itself and the chemical evolution of the universe. The earliest epochs of the universe, as we've previously explored, were dominated by hydrogen and helium, the two simplest and most abundant elements created during Big Bang nucleosynthesis. However, these lightweight elements largely lack the physical properties needed to condense into solid matter necessary to build planets, especially rocky worlds like Earth. The formation of planets, particularly those with solid surfaces, depends critically on the presence of elements such as carbon, oxygen, silicon, iron, magnesium, and other metals. These elements form dust grains, microscopic solid particles that serve as the foundational building blocks of planetesimals, and, after collisions and coagulation, the planets themselves. Without metals, the universe would be an expanse filled only with stars and gas, barren of the complex solid bodies that define planets. This fundamental fact constitutes the metallicity problem. The universe's original composition contained essentially no metals, so planets could not have formed until stellar processes synthesized these elements and dispersed them into space. The first stars, population 3 stars, were metal-free by definition. Their brief, turbulent lives culminated in explosive supernovae that synthesized and sprayed the first heavy elements into their surroundings. This initial chemical enrichment began the slow transformation of the cosmos from a metal-poor to a metal-enriched environment. Over successive generations, stars recycled this enriched material, progressively increasing the galactic metallicity and enabling the formation of dust and molecules critical for efficient cooling in molecular clouds. This evolving metallicity influenced where and when planets could begin to form. For instance, astronomers observe a strong correlation today. Stars with higher metallicities are significantly more likely to harbor planets. This trend emerges clearly in exoplanet surveys, showing that stars rich in metals have higher occurrences of both rocky planets and gas giants. Metallicity also affects the architecture of planetary systems, influencing planet sizes, compositions, and orbital arrangements. Early in cosmic history, insufficient metallicity meant there was simply a lack of solid material to build planetesimals efficiently. Even if gas giant planets could form from gravitational instabilities in massive disks, the creation of terrestrial planets was greatly inhibited. Moreover, the formation of dust grains and complex molecules, which aid the cooling and fragmentation of gas clouds, is tightly tied to available metals, making it challenging for planet formation in low metallicity environments. Scientists attempt to pinpoint a metal enrichment threshold, often expressed as a critical metallicity, below which planet formation is inefficient or impossible. Studies suggest this threshold to be roughly 1/100th to 1,000th of the Sun's metallicity, though the exact value remains under active investigation. This threshold defines a cosmic boundary, demarcating when environments became fertile enough to foster the birth of planets. Understanding the metallicity problem is essential not only for clarifying planet formation chronology, but also for refining our search for ancient exoplanets. It implies that planets likely did not exist around the earliest stars directly, but emerged later, once the universe accumulated sufficient heavy elements through repeated cycles of stellar birth and death. Furthermore, metallicity influences the abundance and properties of dust grains, which affect the radiative transfer within protoplanetary disks and, consequently, the thermal environment where planets assemble. The chemistry of metals also underpins the formation of organic molecules, which bear profound implications for the possibility of life elsewhere in the cosmos. In summary, the metallicity problem underscores a fundamental cosmic truth. Planets are products of a universe shaped by stellar alchemy. Without the heavy elements forged in the cores and explosive deaths of stars, planets, especially rocky and potentially habitable ones, could not exist. This chemical enrichment set the stage for the rise of planetary systems, intertwining stellar evolution, galactic formation, and ultimately, the history of life. As we move forward in this exploration, we will delve into the theoretical limits of planet formation in early cosmic structures, like mini-halos, and explore whether planets could have taken shape at the very edges of galaxy formation, teasing apart the intricate timeline of planets versus galaxies in the early universe. As we venture into the rich and intricate tapestry that is cosmic evolution, a fascinating question arises. Could planets have formed in mini-halos before galaxies fully assembled? Mini-halos are small, gravitationally bound aggregates of dark matter and gas, significantly less massive than the mature galaxies we are familiar with today. Understanding whether planetary formation could have occurred within such primordial structures challenges our comprehension of early universe conditions and pushes the boundaries of astrophysical theory. To begin, we must grasp what mini-halos are and how they fit into cosmic evolution. These small, dark matter halos, with masses typically between 1 million and a few billion solar masses, are believed to be the earliest sites where baryonic matter, the normal matter consisting of protons, neutrons, and electrons, could cool and condense. They arose due to the growth of primordial density fluctuations seeded by quantum effects during inflation. Crucially, mini-halos provided the gravitational wells needed to attract and accumulate hydrogen and helium gas, creating potential cradles for the first stars. Given their relatively small mass, the internal conditions of mini-halos were markedly different from those of larger galactic halos. Their gravitational pull was weaker, resulting in generally lower gas densities and higher susceptibility to feedback processes such as stellar radiation and supernova-driven winds. These factors complicate the environment for both star and planet formation. The possibility of planet formation in mini-halos hinges on several intertwined physical and chemical considerations. First and foremost is the issue of metallicity. As established earlier, metals, the elements heavier than helium, are essential for forming dust grains, which themselves are the foundational seeds for planet formation. However, mini-halos formed very early in cosmic history, often before the interstellar medium was significantly enriched by the supernovae of the first stars. In many cases, their initial gas was metal-poor or even pristine, lacking the raw materials to build planetary cores. Yet, theoretical models suggest that some mini-halos could have undergone localized star formation, especially the formation of population 3 stars. The deaths of these massive stars through supernova explosions could rapidly enrich localized regions with metals and dust. This localized enrichment potentially provides transient windows when metal-enriched gas exists within certain mini-halos, temporarily creating environments more favorable to planetary formation. Another critical factor is the cooling efficiency of the gas within mini-halos. Cooling is essential. It allows gas clouds to lose thermal energy, collapse under gravity, and fragment into dense clumps where stars and planets may form. In metal-poor environments, the primary coolants are molecular hydrogen and, to a lesser extent, helium hydride ions. These species are significantly less efficient coolants compared to metal lines and dust emission, leading to warmer gas temperatures and larger characteristic fragment masses. Consequently, fragmentation tends to produce massive stars rather than the lower mass stars more conducive to hosting planetary systems. Moreover, the dynamical environment in mini-halos is often turbulent and shaped by intense radiation and feedback from early stellar populations. Such conditions can disrupt protoplanetary disks or prevent their formation altogether. High-energy photons emitted by massive stars contribute to ionizing gas, producing photoevaporation effects that can erode disks, shortening the timescales over which planets might assemble. Gravitational instability within massive gaseous disks in mini-halos could, in principle, lead to rapid formation of massive planets or brown dwarfs. However, this mode of formation likely requires specific mass and temperature conditions, which may be rare or short-lived in mini-halo environments. Recent cosmological simulations explore these processes, investigating scenarios where pockets of enriched gas in mini-halos might cool efficiently enough to support star clusters and, subsequently, planet formation within those stellar systems. These simulations indicate that while not entirely precluded, planet formation in mini-halos would be exceptional, occurring only in limited metal-enriched niches following early supernovae events. From an observational standpoint, direct evidence for planet formation in mini-halos remains elusive due to their small size, faint emission, and the vast distances involved. The sensitivity and resolution required to detect protoplanetary disks or planets in these early epochs are beyond current capabilities. In summary, while mini-halos serve as the primordial gravitational seeds for the cosmic web and the formation of the first stars, their potential to host the complex processes leading to planet formation is severely constrained by low metallicity, heating, and feedback mechanisms. Theoretical limits established by cooling physics, metal enrichment timescales, and dynamical effects suggest that planet formation in mini-halos likely occurred only after sufficient chemical processing of the interstellar medium, predominantly in environments more evolved than pristine mini-halos. This understanding situates the emergence of planets more securely within the realm of mature protogalactic structures, formed after and often within the growing galaxies themselves. Yet, this boundary remains a vibrant area of research, continuously refined by advances in simulation techniques and tomorrow's observations, offering tantalizing glimpses into how the earliest worlds may have come to be amid the universe's infancy. In the following chapters, we will dive deeper into the cosmic chemistry of dust and molecules, the essential building blocks of planets, and examine how these materials arise and evolve in the early universe's nascent environments. To truly understand how planets emerge in the cosmos, it is essential to delve into cosmic chemistry, the profound processes that transform simple atoms into the complex dust and molecules that serve as the primordial building blocks of planets. Dust grains and molecules are the foundational seeds within interstellar clouds and protoplanetary disks that coalesce and grow, setting the stage for planet formation. Exploring their origins and evolution unveils the chemical pathways that link the earliest stars and galaxies to the worlds we see today. The universe's chemical journey began with the simplest elements forged in the Big Bang: hydrogen and helium, with trace amounts of lithium. However, these light elements alone lack the complexity and solidity needed to form planets. The cosmos required heavier elements: carbon, oxygen, silicon, iron, and others, produced in the hearts of stars and ejected during supernova explosions and stellar winds. These metals, once scattered into space, initiated the formation of dust grains and complex molecules. Dust grains are tiny solid particles composed chiefly of metals and their compounds, silicates, carbonaceous materials, iron, and ices in cooler regions. These minuscule solids perform a multitude of roles. They provide the surfaces upon which molecules form and react, assist in cooling interstellar gas by absorbing and re-radiating energy, and catalyze the aggregation process that leads to planetesimals, the kilometer-sized precursors to planets. Dust grains also act as the fundamental solid building blocks in protoplanetary disks, where their coagulation and growth underpin the initial stages of planet formation. Molecules such as molecular hydrogen, H2, water, H2O, carbon monoxide, CO, ammonia, NH3, and a variety of organic compounds additionally enrich the chemical landscape. These molecules are essential coolants, facilitating the loss of thermal energy in collapsing molecular clouds, allowing dense regions to fragment and form stars and planets. Furthermore, complex organic molecules, synthesized on dust grain surfaces or within gas phases, lay intriguing groundwork for prebiotic chemistry, linking cosmic evolution to the potential origins of life. But how do these dust grains and molecules arise, especially in the early universe where metals were scarce? Initially, in the aftermath of population 3 supernovae, metals began condensing into dust grains within the cooling ejecta. Despite the violence of these explosions, they provided the first reservoirs of solid material. The efficiency and composition of early dust production remain subjects of vibrant research, as these dictate early star-forming cloud environments and influence the timeline of planet formation. As these metals and dust grains mix with the surrounding interstellar medium, molecular clouds rich in dust form, setting the scene for the next wave of star and planet formation. Within the dense and shielded interiors of these clouds, molecular formation is enhanced as dust grains catalyze reactions and protect molecules from destructive ultraviolet radiation. In protoplanetary disks, dust grains grow through successive collisions and sticking, evolving from submicron sizes to pebbles, then to planetesimals, progressively building planetary cores. Molecules trapped in icy mantles on dust particles participate in creating diverse chemical compositions, shaping the inventory of solids and volatiles in emerging planetary systems. Importantly, the abundance and characteristics of dust and molecules evolve with the universe's metallicity. In low metallicity early galaxies and star-forming regions, dust content is reduced, affecting cooling rates and the efficiency of planet-building processes. Conversely, metal-rich environments like the Milky Way today are highly conducive to complex dust and molecular chemistry, enhancing the prospects for planet formation. Observations across multiple wavelengths, infrared, submillimeter, and radio, have revealed the presence of dust and molecules in both nearby and distant galaxies, tracing their distribution and evolution across cosmic time. Facilities like ALMA have detected dust emission and molecular lines in galaxies as distant as those formed within the first billion years of the universe, confirming that the ingredients for planet formation existed surprisingly early. Understanding cosmic chemistry thus bridges the formation of stars and planets, linking nuclear processes deep within stars to the tangible matter that eventually assembles into worlds. This rich chemical heritage, seeded by generations of stellar evolution, crafts the universe's material diversity and complexity. As we move forward, we will examine how observations constrain the presence of planets around the oldest stars and look into specific ancient planetary systems within the Milky Way, offering clues about planetary survival and formation amidst the galaxy's ancient halo and globular clusters. Delving into the oldest stars and their planetary systems offers a compelling window into the universe's formative eras and provides tangible constraints on when and where planets first appeared. These ancient stars serve as living fossils, preserving within their atmospheres the chemical signatures of the early cosmos. Studying them, and any planets orbiting them, helps astronomers trace the timeline of planetary formation and assess the conditions that prevailed in the universe's infancy. Stars with extremely low metallicities, often called population 2 stars, are among the oldest observable objects in our galaxy. They formed from gas clouds only slightly enriched by the first star's supernovae and thus retain the elemental fingerprints of that early enrichment. Over the past few decades, astronomers have discovered numerous such metal-poor stars in the Milky Way's halo and its globular clusters. Their ages approach 12 to 13 billion years, making them invaluable proxies for conditions in the early universe. One key question is whether planets form around these ancient stars despite their low metal content. Exoplanet detection techniques, including transit photometry, radial velocity measurements, and gravitational microlensing, have increasingly targeted metal-poor stars to seek answers. Empirical studies reveal a pronounced correlation between stellar metallicity and giant planet occurrence. Stars richer in heavy elements are more likely to host gas giants. This trend reinforces the so-called metallicity effect. Nevertheless, smaller rocky planets appear less influenced by stellar metallicity, suggesting that terrestrial planets might form even around relatively metal-poor stars, though likely with differing abundances and compositions. The discovery of planets orbiting stars with metallicities significantly below solar gives credence to the idea that planet formation was already underway in environments enriched by early cosmic nucleosynthesis, but still primitive by today's standards. For instance, the system around the ancient star Captain's star, estimated to be about 11 billion years old, contains at least 2 super-Earths, indicating old planetary systems do exist. Additionally, rogue planets, planets not gravitationally bound to any star, could represent primordial relics, though their origins remain speculative. They might either be ejected from young planetary systems or form in isolation under unique conditions. Globular clusters, dense collections of old stars, also provide clues. Despite their age, planets in such clusters are rare discoveries, possibly due to the intense stellar interactions disrupting planetary orbits or differences in metallicity influencing planet formation rates. The few candidate planets identified in clusters like M4 or 47 Tucanae point to complex formation and survival scenarios. Spectroscopic analyses of metal-poor stars contribute further constraints by measuring elemental abundances linked to planet-building materials, such as iron, silicon, magnesium, and carbon. Particularly, the carbon-to-oxygen ratio influences planet composition and geological processes, affecting potential habitability. As observational campaigns progress and detection sensitivity improves, especially with upcoming missions targeting ancient star populations, our empirical framework will tighten. We expect to reveal more about the early epochs of planet formation, the diversity of such planets, and the environments that could nurture them. In conclusion, while the oldest known stars exhibit varied and often low metallicity, the accumulating evidence indicates that the potential for planet formation likely emerged relatively early in the galaxy's history. Studying these ancient stellar hosts and their planetary companions provides invaluable anchor points in the cosmic timeline, bridging our theoretical understanding with concrete observational data. The next chapter takes a closer look at some remarkable ancient planetary systems within our own Milky Way's halo and globular clusters, offering case studies that illuminate the possibilities and constraints of planetary survival and formation in the cosmos's oldest environments. The vast and ancient reaches of our own Milky Way galaxy provide a remarkable laboratory for studying some of the oldest planetary systems known, especially those residing in the galactic halo and globular clusters. These celestial environments hold stars that formed early in the galaxy's history, some dating back over 12 billion years, offering invaluable case studies about the origins and endurance of planets amidst some of the most extreme and historic conditions in the cosmos. The Milky Way's halo is an extended, roughly spherical distribution of stars and dark matter enveloping the central galactic disk. It contains many of the galaxy's most metal-poor stars, relics from ancient epochs. These stars often exhibit low metallicities, reflective of early cosmic times when heavy elements were scarce. Owing to their age and chemical simplicity, halo stars serve as critical proxies for investigating early planet formation processes in metal-poor environments. Remarkably, a growing number of exoplanets have been discovered around halo stars, challenging earlier assumptions that planets predominantly form around metal-rich stars. For instance, Kapteyn's star, a halo star approximately 11 billion years old, hosts at least 2 super-Earth exoplanets. Their existence demonstrates that planet formation could proceed efficiently in environments with metallicities lower than the Sun's, although perhaps with different planetary characteristics and formation pathways. Beyond the halo, globular clusters present another fascinating venue for examining ancient planetary systems. These dense star clusters, containing hundreds of thousands to millions of stars tightly bound by gravity, are among the oldest structures orbiting the Milky Way. Many globular clusters date back to nearly the age of the galaxy itself, and therefore host some of the oldest stars. Despite intensive searches, the detection of planets in globular clusters has proven challenging. Early surveys, including those targeting the 47 Tucanae cluster, yielded no confirmed exoplanets, leading to hypotheses that high stellar densities and dynamical interactions might hinder planet formation or destabilize planetary orbits. The intense radiation environment and gravitational perturbations in these clusters create potentially hostile conditions for planet retention. Nonetheless, a few compelling planetary candidates have been identified. Notably, the pulsar planet discovered around PSR B1620-26 in the globular cluster M4 represents one of the oldest known planets, sometimes dubbed the Methuselah planet, with an estimated age of about 12.7 billion years. This planet likely formed through complex evolutionary pathways involving stellar remnants, underscoring that planet formation and survival in globular clusters might occur under extraordinary circumstances. Chemical composition analyses of globular cluster stars provide further insights. While they are generally metal-poor, certain clusters show a small spread in metallicities or enrichments in specific elements, which might influence the prospects for planet formation. Comparing these chemical environments with planet occurrence rates informs models of planet formation thresholds in early stellar populations. The survival of planets in both the halo and globular clusters depends on stable orbits amid a gravitationally dynamic environment. Stellar encounters, tidal forces, and radiation fields can disrupt or strip planetary systems, particularly on long timescales. Yet the existence of ancient planets in these environments attests to planetary resilience and offers clues about the dynamical histories of these stellar populations. Studying planets in such ancient and extreme environments bridges astrophysical theory with empirical observation. It challenges our understanding of planetary system formation, survival, evolution, and diversity across cosmic time. These case studies also expand our grasp of where habitable conditions might arise, considering that planets orbiting ancient stars might harbor conditions potentially favorable for early life. As technology advances and observational methods improve, particularly with upcoming telescopes and precise instrumentation, the frontier of detecting and characterizing planets in these remote and venerable regions will widen. By piecing together the story of ancient planetary systems in the galactic halo and globular clusters, we deepen our comprehension of the cosmos' earliest eras and the inception of worlds that may parallel our own. The rapidly advancing field of exoplanetary science has revolutionized our understanding of planetary systems since the first confirmed detections in the 1990s. Yet one of the most intriguing questions remains: do planets exist around the oldest stars in our galaxy, those that formed during the universe's infancy? The answer to this question offers a crucial insight into the epoch when planet formation began and how robust planetary systems are in ancient, metal-poor environments. Exoplanet surveys utilize various techniques to detect planets, from the transit method, where a planet briefly blocks a fraction of a star's light, to radial velocity measurements that detect the gravitational tug of a planet on its host star, as well as microlensing and direct imaging. Each method offers different sensitivities and biases, making the search in older stellar populations both challenging and rich with promise. Among the oldest stars, especially those in the halo of the Milky Way and globular clusters, detection of exoplanets has been sparse but not absent. One key hurdle is that many ancient stars are metal-poor, and early observations indicated a lower incidence of giant planets around such stars. This correlation aligns with the metallicity effect, which shows stars with higher heavy element abundances are more likely to host gas giants. However, smaller rocky planets appear less sensitive to metallicity, suggesting terrestrial planets could form even in older, metal-deficient systems. Promising discoveries have emerged. Planets orbiting ancient metal-poor stars like Captain Star, an estimated 11 billion-year-old halo star, challenge earlier assumptions. These super-Earths demonstrate that planet formation processes were active quite early in the galaxy's history. Moreover, studies of low metallicity stars in the solar neighborhood suggest that terrestrial-sized planets may be common, even when heavy element content is reduced. Despite their rarity, planets in globular clusters have tantalized astronomers. Early attempts to find planets in 47 Tucanae, one of the closest and most studied globular clusters, yielded null results. The cluster's dense stellar environment likely disrupts planetary orbits. Yet pulsar planets, such as the one in the globular cluster M4, show that planets can exist in aged and dense regions, although possibly through exotic formation pathways. Notably, the microlensing method has revealed free-floating, or rogue, planets that could potentially be ancient, though their origins are debated. These planets, not bound to any star, reveal how planetary bodies may form and survive even outside conventional systems. Surveys are now pushing toward detecting planets around extremely metal-poor stars beyond just the solar neighborhood, leveraging instruments with improved sensitivity and long-term observation campaigns. This expanded search continues to test the thresholds of planet formation and survival in ancient galactic environments. In summary, exoplanet surveys increasingly indicate that planets do form and survive around some of the oldest stars, albeit with variations influenced by metallicity and local environment. These findings imply that planet formation has a deep-rooted history in the galaxy, correlating with, but not strictly limited to, metallicity. As technology and observation techniques continue to advance, especially with future space missions and extremely large telescopes, we anticipate a more detailed census of retrograde planetary systems, shedding light on the dawn of planet formation across cosmic time. This ongoing exploration beckons us toward alternative formation scenarios, rogue planets, and the intriguing possibility of planets forming in isolation from galaxies, themes we will explore in the next section. As our exploration into the origins of planets deepens, we arrive at intriguing alternative scenarios that challenge conventional thinking, particularly the concept of rogue planets and planetary formation isolated from galactic environments. These unconventional pathways open windows into how planetary bodies might exist outside the context of traditional star systems and galaxies, stirring profound questions about their origins and prevalence in the cosmos. Rogue planets, also known as free-floating or interstellar planets, are planetary mass objects not gravitationally bound to any star. Instead, They drift through interstellar or even intergalactic space, untethered and solitary. Early theoretical predictions proposed their existence, but technological limitations delayed their observational confirmation. Today, advancements in microlensing surveys and infrared observations have identified several candidates, suggesting that rogue planets may number in the billions within our own galaxy. The origin of rogue planets poses an astrophysical puzzle. Two primary hypotheses attempt to explain their existence. One posits that these planets formed in typical protoplanetary disks around stars, but were subsequently ejected due to gravitational interactions, stellar encounters, or dynamical instabilities. The other suggests that some rogue planets formed in isolation, collapsing directly from the gas in molecular clouds without ever becoming bound to a star. If rogue planets can form independently of stars, this implies that planet formation may, in some form, predate or at least be parallel to star formation in certain regions. This possibility bears significance for early cosmic history, where dense gas clumps in mini-halos or nascent galaxies could collapse directly into planetary mass objects, seeding the universe with isolated planetary bodies before or alongside traditional star systems. Such isolated formation scenarios rely on specific conditions. The gas cloud must be cool and dense enough to overcome thermal pressure and fragment into small masses. In the modern cosmos, this process is rare due to efficient fragmentation favoring star formation. However, in the metal-poor environments of the early universe, with different cooling physics dictated by molecular hydrogen and absence of dust, the pathways to isolated planet formation might have unique parameters. The dynamics of galactic evolution also factor into these alternative scenarios. Interactions, mergers, and tidal forces in the vast cosmic web can strip planetary systems from their host galaxies, producing a population of rogue planets on intergalactic trajectories. These wandering worlds may populate intergalactic space, invisible to conventional stellar-based surveys, and potentially vastly outnumber planets bound within galaxies. Environmental isolation impacts not just the mechanics of formation, but also the potential habitability of these rogue planets. Without a host star's illumination and heat, such planets would be cold and dark. Yet, intriguing theoretical models explore internal heating mechanisms, radioactive decay, and residual heat from formation that could sustain subsurface oceans beneath thick ice layers, creating niches potentially hospitable to life. Moreover, rogue planets challenge our understanding of planet detection and demographic estimates. Their faint emission and isolation make them elusive targets, prompting the development of sensitive microlensing campaigns and future instruments optimized for detecting faint, isolated planetary bodies. The presence of rogue planets and formation pathways isolated from galaxies broadens our conception of planetary prevalence and diversity. These alternative scenarios suggest that planets need not always be byproducts of mature star systems within galaxies, but can arise from a rich spectrum of cosmic environments and evolutionary histories. Ultimately, the study of rogue planets and isolated formation sheds light on the universe's capacity for complexity and surprises, forcing us to reconsider the boundaries of planet formation. As technology advances and surveys become more sensitive, especially with upcoming facilities like the Nancy Grace Roman Space Telescope and the Vera Rubin Observatory, we anticipate uncovering the true population and nature of these enigmatic wanderers. Looking ahead, these insights set the stage for hypotheses and broader debates about the fundamental chronology of cosmic structure formation. Could, in principle, planets precede galaxies, or are galaxies indispensable cradles of planetary birth? This question will be the focus of our next chapter, where we synthesize evidence and confront the limits of current understanding. The profound question of whether planets can precede galaxies challenges our understanding of cosmic chronology and the hierarchical structure formation that shapes the universe. It sits at the intersection of astrophysics, cosmology, and planetary science, inviting us to reconsider traditional assumptions and explore the theoretical boundaries of how and when planets might emerge relative to the first galaxies. Conventionally, galaxies are viewed as the fundamental building blocks of the cosmos, massive gravitationally bound systems hosting billions of stars. Within these stellar populations, protoplanetary disks form around young stars, setting the stage for planet formation. Thus, galaxies have long been considered indispensable cradles for planets, providing the necessary environment, enriched chemical compositions, and stable gravitational settings. This traditional view positions galaxies unequivocally earlier in the cosmic timeline, with planets as later byproducts of galactic evolution. However, as our knowledge deepens about the early universe's small-scale structure and the varied pathways of cosmic evolution, several hypotheses have sought to challenge or nuance this narrative. One core idea emerges from considerations of minihalos and isolated star formation prior to large-scale galactic assembly. These small, dark matter halos, forming within a few 100 million years after the Big Bang, could potentially host stars and, under certain conditions, planetary systems. If so, planets might have born earliest in these proto-galactic structures, preceding the development of fully fledged galaxies. Yet, this theoretical possibility is constrained by several fundamental considerations. Minihalos and their contained primordial gas clouds experienced limitations in metallicity. The essential heavy elements for planet formation were scarce or absent at these times. Since metals are synthesized and dispersed primarily by supernovae, the temporal sequence suggests first stars, then enrichment, then planet formation, with galaxies forming concomitantly by merging and aggregating these structures. Metals are also crucial for cooling gas, enabling disks to fragment and coalesce into planetesimals. Without metals, the efficiency and likelihood of planet formation diminishes sharply. Some advanced models propose that under rare, localized enrichment events, such as a population 3 supernova exploding within a mini-halo, the metallicity could cross a critical threshold sufficient to enable dust and solid grain formation shortly before, or in parallel with, the coalescence of larger galactic structures. This leads to a scenario where planets might exist in isolated pockets predating established galaxies. However, the survival and observational prospects of such planets remain speculative. Another avenue of debate examines the existence of rogue or free-floating planets that may form outside traditional star systems, possibly originating in isolation or via ejection. Could such planets have formed in the intergalactic medium or within nascent mini-halos before galaxies matured? While intriguing, these objects still require conditions favoring dust and molecule formation, ultimately tied to stellar nucleosynthesis, and hence the prior existence of stars and galaxies. Philosophically, the idea that planets could precede galaxies challenges hierarchical cosmic structure notions, but compels us to recognize that the universe is not a strictly linear system. Cosmic evolution is complex and multi-scaled. Small-scale structures seed larger ones, and intricate feedback loops govern chemical evolution and matter dynamics. Current observational evidence supports the traditional sequence: galaxies forming first, followed by planet formation within metal-enriched environments they enable. Nevertheless, the computational and theoretical frameworks remain flexible, accommodating nuances and exceptional pathways. Debates in this field underscore the necessity of further observations, especially with new instruments capable of probing the universe's earliest epochs, where direct evidence of the first stars, protogalaxies, and possibly planets may be found. These include the James Webb Space Telescope, the Extremely Large Telescope, and next-generation radio arrays, which may unveil the first traces of planet formation or identify molecular and dust signatures in unexpected early contexts. In summary, while the principle that planets precede galaxies remains contentious and largely theoretical, the hypothesis fuels vital research that deepens our grasp of cosmic origins. It drives the frontier of astrophysics toward deciphering the universe's most profound mysteries. How and when did the first worlds take shape? And what conditions governed their inception in the majestic cosmic dance that began nearly 14 billion years ago? As we synthesize the diverse threads of observational data, theoretical models, and cosmic chemistry, we shall next chronicle the emerging timeline of the earliest galaxies and planets, weaving together evidence from multiple disciplines to narrate the chronology of the universe's first worlds. Synthesis is the bridge that connects our understanding of the universe's origin, early evolution, and the emergence of the complex structures that populate it today. Having traversed the vast spectrum of cosmic time, from the Big Bang through the appearance of the first atoms, the cosmic dark ages, and the igniting of the initial stars, to the assembly of galaxies and the dawn of planetary systems, it's essential to weave these threads into a coherent chronology. This timeline not only frames when galaxies and planets formed, but also illuminates their intricate interdependence. The journey begins approximately 13.8 billion years ago with the Big Bang, creating a primordial universe filled primarily with hydrogen and helium. Over the first several 100,000 years, as the universe expanded and cooled, these fundamental elements formed neutral atoms during the epoch of recombination. This moment permitted photons to travel freely, leaving behind the cosmic microwave background radiation, a snapshot of the universe's infancy. Following recombination, the universe entered the cosmic dark ages, a prolonged era devoid of luminous sources. Gravity worked silently on the slight irregularities in matter distribution, growing denser pockets within dark matter halos known as minihalos. These structures became the earliest sites where gas cooled and contracted sufficiently to trigger the formation of the first stars, the population 3 stars. These massive metal-free stars are pivotal, as they manufactured the first heavy elements through nucleosynthesis and dispersed them via their explosive deaths, setting the chemical stage for subsequent cosmic evolution. The enrichment of the interstellar medium with heavy elements, a process termed metallicity, was critical. Metals function as the crucial building blocks for dust grains and molecules, enabling more efficient cooling of gas clouds and fostering the formation of protoplanetary disks around young stars. These disks, rich in dust and metals, are the birthplaces of planets. Galaxies, which formed through the hierarchical merging and growth of dark matter halos, serve as the gravitational sanctuaries that concentrate metal-enriched gas, stars, and dust. The first galaxies appeared several 100 million years after the Big Bang, exhibiting intense star formation but lower metallicities than present-day galaxies. Galaxies, in all their complexity, provided the environments where multiple generations of stars could evolve, enriching their surroundings to levels conducive for planet formation. Astrophysical observations, combined with sophisticated simulations, affirm that the conditions requisite for planet formation, adequate metallicity, protoplanetary disks, and stable stellar environments, emerged only after several generations of stars had lived and died. Consequently, planets began to form predominantly after galaxies were well underway in their assembly, not before. While theoretical possibilities and niche scenarios consider planet formation in mini-halos or isolated pockets prior to galaxy formation, these are likely exceptions rather than the norm. constrained by low metallicities and energetic environments hostile to sustained planetary assembly. Likewise, exotic cases such as rogue planets challenge the idea that planets strictly adhere to galactic timelines. Yet even these ultimately depend on prior star and galaxy formation for their elemental foundation. In our Milky Way and other nearby galaxies, studies of ancient stars in the halo and globular clusters, some of the oldest stellar populations, reveal that planets do exist around stars formed when the universe was young but chemically evolved enough. This again links the timeline of planet formation closely with the progressive chemical enrichment wrought by successive stellar generations within galaxies. In sum, the chronology of the first galaxies and planets is a staggered, interwoven process. Galaxies provide the gravitational, chemical, and environmental frameworks necessary for planetary systems to emerge. Planets form not in isolation, but as natural outgrowths of galactic evolution and chemical enrichment. As our technological prowess grows with forthcoming observatories such as the James Webb Space Telescope and the Extremely Large Telescope, we stand at the threshold of unveiling this timeline in unprecedented detail. We anticipate direct observations of the earliest galaxies, nascent stars, and potentially even primordial planetary systems, refining this chronology and deepening our grasp of the universe's origin story. This synthesis prepares us to confront the remaining uncertainties and open questions in early cosmic evolution, the frontiers where our understanding still falters and new discoveries eagerly await. As we stand at the crossroads of cosmic understanding, gazing back across billions of years to the universe's earliest moments, it is humbling to recognize how much there remains to discover about early cosmic evolution. Despite remarkable advances enabled by sophisticated telescopes, simulations, and theoretical breakthroughs, key questions linger, enigmatic gaps that challenge astrophysicists and cosmologists alike. These open questions define the frontier of the quest to understand the origins of galaxies, stars, planets, and the conditions that ultimately gave rise to life. One fundamental mystery revolves around the nature and properties of population 3 stars themselves. Although their existence is theoretically well supported, direct observational evidence remains elusive. We still do not know precisely their mass distribution, lifespans, or multiplicity, nor the exact mechanisms governing their formation in the metal-free early universe. Determining these parameters is essential, as population 3 stars shaped the universe's initial chemical enrichment and initiated the formation of complex structures. The timing and topology of cosmic ionization are also active areas of inquiry. This epoch, when ultraviolet radiation from the first stars and galaxies ionized the intergalactic medium, profoundly influenced the later formation of galaxies and planets. Yet, questions remain about which sources dominated reionization, the duration of the process, and how patchy or uniform it was across cosmic volumes. Another profound open question concerns the metal enrichment in the earliest galaxies and minihalos. How rapidly and uniformly were heavy elements dispersed? Could small pockets of pristine gas survive amid the expanding influence of supernovae? These details affect the cooling processes critical for star and planet formation and the chemical diversity of the first stellar populations. Similarly, the initial mass function, IMF, in the earliest epochs, how the masses of the first stars were distributed, influences the feedback processes that regulate the growth of galaxies. The transition from massive, short-lived population 3 stars to lower mass population 2 stars involves complex physics still not fully understood. On the planetary front, we lack firm empirical data on when and how the very first planets arose. Were there niches allowing planets to form around second or even first-generation stars? To what extent did the low metallicity and intense radiation environments constrain early planetary systems? The discovery of ancient exoplanets is tantalizing, but far from comprehensive. The role of dust and molecules in the earliest dense clouds also remains a debate. Questions about the efficiency of early dust grain production, their compositions, and survival through turbulent early environments impact our models of star and planet formation. Furthermore, the influence of dark matter on small scales, such as in minihalos, and its interactions with baryonic matter pose unresolved theoretical challenges. How this shapes the gas collapse necessary for the first luminous objects is critical for our grand narrative. Lastly, observationally, pushing the boundaries of detection toward the cosmic dawn remains an immense challenge. We seek to observe the faint light from the very first galaxies and possibly nascent planetary systems, hindered by redshift effects, cosmic opacity, and instrumental limitations. These open questions drive the development of next-generation technology and inform theoretical ambitions. The answers will deepen our insight into the universe's earliest chapters, painting a more complete portrait of cosmic history that encompasses not only the grandest structures, but also the subtle emergence of worlds and ultimately life. This compels us to look ahead with anticipation toward future observatories, like the James Webb Space Telescope, Extremely Large Telescope, and others, that will unlock the secrets veiled in the earliest epochs of cosmic time. In the coming chapters, we will explore these future technologies and how they promise to transform our understanding of the ancient universe and our place within it. Peering ever deeper into the cosmos and further back in time requires technological marvels that push the boundaries of engineering and scientific ingenuity. The quest to uncover when and how the first planets and galaxies formed hinges on observations that challenge current capabilities, propelling the development of next-generation observatories. Among the vanguard of such instruments are the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and a cadre of upcoming facilities set to revolutionize our understanding of the early universe. Launched with great anticipation, the James Webb Space Telescope stands as the premier space-based observatory designed to observe infrared light, the key to unlocking the ancient universe. Unlike its predecessor, the Hubble Space Telescope, JWST's larger mirror and advanced instruments enable exquisite sensitivity at longer wavelengths, vital for detecting faint galaxies whose light has been stretched by cosmic expansion, and probing the atmospheres of exoplanets in unprecedented detail. JWST's capabilities allow it to pierce the cosmic veil of dust and gas that obscures many star-forming regions, unveiling galaxies formed within a few 100 million years after the Big Bang. Its instruments can characterize the chemical makeup, star formation rates, and structural properties of these early galaxies, directly addressing many pressing questions about the timeline of cosmic evolution. Moreover, JWST can study protoplanetary disks around young stars, providing insights into the environments where planets form. Complementing JWST are the ground-based extremely large telescopes, such as the ELT, under construction by the European Southern Observatory. With its giant segmented mirror spanning 39 meters, the ELT represents the largest optical infrared telescope ever built. Its exceptional resolving power and light-gathering ability will permit detailed observations of individual stars in distant galaxies and the detection of the faintest signatures of planet-forming disks and exoplanets. The ELT's advanced adaptive optics systems will correct atmospheric distortions, enabling astronomers to achieve nearly diffraction-limited imaging from the ground. This is pivotal for disentangling crowded stellar populations in ancient globular clusters, probing the kinematics and composition of early galaxies, and conducting sensitive exoplanet surveys targeting the oldest stars. Beyond JWST and ELT, a suite of other next-generation facilities will enhance our cosmic reach. The 30-meter telescope, Secton TMT, and Giant Magellan Telescope, GMT, promise similar revolutionary improvements in sensitivity and resolution. Meanwhile, radio observatories like the Square Kilometer Array, SKA, will explore neutral hydrogen's distribution during the cosmic dawn, offering complementary views of the intergalactic medium and galaxy formation. Simultaneously, dedicated exoplanet missions such as the Nancy Grace Roman Space Telescope will expand our ability to detect and characterize exoplanets, including ancient planetary systems. High-contrast imaging technologies and space interferometers on the horizon may even enable the study of planetary atmospheres for biosignatures, transforming the search for life in the cosmos. These future technologies will not only refine the chronology of the first galaxies and planets, but will also confront current theoretical uncertainties, resolve the nature of population 3 stars, and potentially detect the earliest planetary systems. The expected synergy between space and ground-based observatories will capitalize on their complementary strengths across multiple wavelengths. In essence, JWST, ELT, and their successor observatories herald a new golden age in astronomy. They empower humanity to peer deeper, see clearer, and understand finer details of the universe's first billion years than ever before. Through their eyes, we will edge closer to answering the age-old question of how the vast cosmic tapestry evolved from primordial simplicity to the rich complexity that includes countless galaxies and worlds, and perhaps even the cradle of life itself. With these powerful tools soon operational, the next frontier awaits. The continuing search to understand our place in a universe populated not only by ancient galaxies, but also by ancient worlds. The final chapter of our journey, The Search Continues, invites us to reflect on this ongoing quest and the profound discoveries yet to come. As we reach the culmination of our cosmic journey, reflecting on the vast epochs that have shaped the universe and considering the intertwined emergence of the first galaxies and planets, we find ourselves poised on the edge of discovery. The quest to understand our place among ancient worlds is far from over. It is an ongoing saga propelled by ever-advancing technologies, relentless curiosity, and profound questions about origins, existence, and cosmic context. From the silent epoch of the cosmic dark ages, through the blazing lives and deaths of the first generation of stars, to the assembly of the earliest galaxies brimming with metals, the essential building blocks of planets, the universe has fashioned environments ripe with potential. The planets and stars we observe today, including our own solar system, are heirs to this magnificent cosmic inheritance. Yet, how many ancient worlds await discovery? How widespread are planets around the galaxy's eldest stars, or even beyond in unseen realms? These questions challenge us to refine our instruments and expand our reach. Upcoming observatories, such as the James Webb Space Telescope, the Extremely Large Telescope, and the Nancy Grace Roman Space Telescope, promise to unveil previously hidden corners of the universe, detecting the faint signals of the earliest galaxies, nascent stars, and potentially primordial planetary systems. Apart from direct observation, theoretical advancements and simulations enable us to explore the uncharted territories of cosmic history, testing hypotheses about star and planet formation under conditions vastly different from those familiar in our celestial neighborhood. The interplay of dark matter, gas physics, and chemical evolution in the early universe remains a rich field of study, shedding light on the cosmic environments that nurtured the first worlds. Within this grand narrative, humanity's place is both humble and extraordinary, We are cosmic descendants of countless generations of stars and planets, shaped by processes that stretch back billions of years and light years. Understanding the first planets and galaxies deepens this perspective, connecting us to the very fabric of the universe's history. The search for ancient worlds is also a search for context, for understanding the conditions that might give rise to life elsewhere, for recognizing the uniqueness or ubiquity of planetary systems like our own, and for situating human existence in the vast cosmic timeline. As technology propels us forward, as we learn from the spectra of distant galaxies and the wobbles of ancient stars, and as our telescopes capture photons traveling since the dawn of time, the universe continues to reveal its story, layer by intricate layer. Our quest is ongoing, propelled by wonder and discovery, reminding us that while we have glimpsed fragments of cosmic history, the universe holds many secrets still to unveil. In this vast cosmos of ancient worlds, our journey is but beginning, and with every step, we draw closer to understanding our place among the stars, guardians and explorers of the universe's oldest stories.